Hello, in this video we're going to talk about electrons and electron shells. In my previous videos we've talked about the basics of the atom and we've addressed protons, neutrons, and electrons. We've talked a little more in depth about protons and neutrons and what they do in the atom. But aside from just stating that electrons are involved with bonding, we haven't really discussed much more than that other than the number of electrons must equal the number of protons for the atom to be neutral. Well, in this video, we're going to get the information that we need to preface before we start bonding atoms to other atoms to form molecules. So, so far we've been taught that electrons reside in this area around the nucleus, the electron cloud. Now, you might think that they just haphazardly exist in this electron cloud, but God made it such that there is intricate detail and specificity in what goes on in this electron cloud. Now, this electron cloud is really organized into things we call orbitals. And I don't want to get too in depth here, getting out of the scope of this course, but suffice it to say the orbitals are basically geometrically constrained regions of space where electrons can exist. That is to say, in easy terms, they're shapes where electrons can be found. Now we can break up the electron cloud into different levels. We have level 1, level 2, level 3, level 4, and so on and so forth. And basically, if we take this sphere, okay, this is 3 dimensions. Let me try to give some depth there. If we take this sphere and we create ever increasing layers of the sphere, and I know these aren't concentric, but kind of this sphere would be level 1, this sphere level 2, this sphere level 3, and so on and so forth. You kind of get an idea of building layer by layer. And not only that, in each level, there are a certain number of and certain types of these orbitals. And we'll talk a little bit about them, but not so much because, like I said, we do not want to get in over our heads here. Now, the orbitals, there are different types. There's an s orbital, there are p orbitals, there are d orbitals, and there are f orbitals. And the arrangement is such that each time we gain a new level, we then bring in a new orbital. So level 1 can only have s. Level 2 can have s, and then we bring in the p's. Level 3, we can have s, we can have p, and we can have d's. And starting in level 4, we have s, p, d, and f. And there are other orbitals other than this, but they never get filled with any of the elements we have that exist in our world or the atoms that man can make in and of themselves in an atom smasher. So we have electrons in this electron shell, and the electron shell is broken up into levels, and each level has different shapes where electrons can reside. Now I'm just going to give you some information here that I'm not necessarily going to explain. Your book may go in a little more in depth, but you really don't need any more than this. So level 1 can only hold 2 electrons. Level 2 can hold up to 8 electrons. Level 3 can hold up to 18 electrons, and level 4 can hold up to 32 electrons. And levels 5, 6, and 7, they're going to max out at 32 anyway because we said we don't go into any orbitals beyond F. So as we go through the periodic table, obviously hydrogen with an atomic number of 1 is only going to have 1 electron. Helium, atomic number of 2, 2 protons, needs 2 electrons, and so on and so forth. Lithium as an atom will have 3 electrons, beryllium 4, boron 5, carbon 6, and so on and so forth. So you can see the organizational structure there with regard to the number of electrons. Now, going back to the periodic table, you may wonder, well, why is the periodic table shaped as such? Why does it have this thin middle? What is going on down here? Why does it have this shape? Well, it's all based upon these orbitals. All right, level 1. We can basically treat this period as level 1. How many electrons can it hold? 2. Level 2 can hold 8. 1, 2, 3, 4, 5, 6, 7, 8. Level 3 can hold 18. Now, we get into a little issue here because we only see 8. And this has everything to do with what your book says and how these shells fill. They don't just fill all in level 1, then all in level 2, then all in level 3. There's actually an order based upon the energies of these orbitals. And I can liken it to a certain situation of dorms rooms in college. Uh, Basically, we all want to expend as little energy as possible. So if you had the option of taking a room, let's say on the 4th floor, that's right next to the elevator, as opposed to a room on the 3rd floor that's all the way down the hall away from the elevator, there's less energy required moving in and out, taking that 4th floor dorm room as opposed to the one on the 3rd floor. And atoms are kind of like that. Filling a d orbital on the 3rd level requires more energy than, hey, that 4th floor S that's right near the elevator. So that's the rationale behind why we just don't fill all of 1, all of level 2, all of level 3, and all of level 4. And it explains the shape of this periodic table. So level 1, 2 electrons total. Level 2, 8 electrons total. Level 3, well, they fill the first 8, the S and P, and then they fill the 4S, which holds 2, and then the 3D, and then the 4P. So as you can see here, we call this section here the S block. Because those are the elements where the electrons, the last electrons to go in, the outermost electrons, are S orbitals. Here we have the P block. The only exception is helium. That only has the S. And here we have the D block. And then at the bottom here, we have the F block. So if you actually count across 2, 8, and then this is 10 wide, so there's your 18. And if we count another 14 here, it gives us 32. So that's where all these numbers come from. But like I said, we don't want to get too in depth here. So on the periodic table, these 2 rows to the left, that's the S block. The 6 to the right, that's the P block. The D block is in the middle, and the F block is in the bottom. So let me erase some of this stuff so we can talk a little bit more about, oh, that's not good at all. This will be a little interesting. We'll just make do with erasing it here, not erasing the periodic table at all. Maybe I'll change colors. I'll go a little red. All right, so we have names for some of these groups. Groups have very similar reactivity. That's why they are given names. And our first group are the alkali metals. Our second group is called the alkali earth elements. And we have the noble gases. And then this group 7A, or 17 in this, are the halogens. So groups have similar reactivity because they have similar electron rearrangements or arrangements, I mean. So in the book, you learn about valence electrons, the electrons on the outside, and basically that is what gives these similar reactivity. Group 1A, or 1 on this scale or on this periodic table, they all have one valence electron. Group 2, or 2A, has two valence electrons. Group 13 or 3A, three valence electrons. Group 14 or 4A, four valence electrons, five valence electrons, six valence electrons, seven valence electrons, and a full valence shell, which we call this rule of 8 octet. So group 1, one valence electron, two valence electrons, 3A is 3, 4A is 4, 5A is 5. You see where I'm going here. Now, so we have these names and we kind of understand that their groups have similar reactivity because of the valence shell that are going to be involved in bonding. And that's why they have similar reactivity, because there's the same number of electrons out there. Now, if I get a somewhat clear area, let's talk a little bit about these valence electrons. Valence electrons. So as I said, 1A equals 1, 2A, 2, 3A, 3, and so on and so forth. 4A, 4 valence electrons, 5A, 5 valence electrons, 6A, 6. Okay. Now, with these number of valence electrons, we go into, or at least the chapter goes into, a discussion about symbolic representations of these valence electrons. And this is the primer for bonding. This is the task and the skill that you need to be able to perform in order to see the bonding and to, in fact, show bonding between atoms. And we call these Lewis dot structures. And they're nothing more than the atomic symbol of the element we're talking about and dots for each of the valence electrons. Now, the only rules here is we need one dot per valence electron, and we put dots on either of the four sides. So I'll draw a little box here, and let's say we have, let's say, oxygen. We'll talk about oxygen. The places where we can put dots are here on the four sides, and each side can have up to 2. The only rule is we do not pair them until we must. Do not pair them until we must. So, group 1A atoms, for example, let's do maybe lithium. We'll do all the period 2 ones. So lithium will have one dot, so we'll just put it on this side. We can put it on the top, we can put it on the left bottom, doesn't matter. Group 2A. All right, so right next to lithium is beryllium. Now beryllium, we need 2 dots, but we can't pair them. Let's not put them all on one side. So we can have them opposite. We can have one on top, one on the bottom, one on the top, and one on the right. It doesn't matter where you put the 2 dots as long as they are not on the same side being paired. Group 3A, boron will have 3 dots. We don't pair them. Group 4A, carbon, we have 1 dot on either side. 5A, this is where we have to pair. And we will, let's say, pair them on the top there. So nitrogen is our example. It has 5 dots. We go around with 1 dot on either side, and then we end up pairing them. 6A is oxygen. we'll have 2 pairs 7A, fluorine with 3 pairs, and then 8A, which will have 8 pairs. I know this is a little bit tight, and I'm sorry about that, but I've run out of space here. Now, all of these Lewis dot structures are the same for the groups. So, lithium will have the 1 dot, just like sodium, potassium, rubidium, cesium, francium. They'll all just have 1 dot, just like lithium. Beryllium with its 2 dots, same as magnesium, calcium, strontium, barium, radium. They will all be similar. They'll all be the same. You just change the symbol, the elemental symbol. Same with boron, aluminum, gallium. 3 dots, carbon, silicon, group 4A, all 4 dots. So once you can draw group 1A through group 8A, the other elements are the same. Now notice, we're not talking about the D block here, also known as the transition elements or transition metals. Okay, we are only dealing with the S and the P blocks. But once you can draw the Lewis dot structures for the first 8 groups, the A groups, then you can draw the dots for any of those elements in those groups. The only exception is helium. Remember, helium is in period 1, so level 1 of the electron shells can only hold 2 electrons. And I'll put it right next to the Lewis dot structure. Helium will have the 2 dots on the one side because that first level electron shell can only hold 2 electrons. So hopefully this helps clear up some of these things. And if it doesn't, please get in touch with me so that I can clear things up for you.